Swayam Prabha. Digital India. Educated India.
Welcome. So, we are in third lecture of module 9. So, we are doing weak form to matrix form. So, I am just detailing the procedure how to compute these matrices for 2D elasticity problem. Now, in the previous lecture we have done the matrix form, where the stiffness matrix and the force vector we have derived, the matrix form for stiffness and force vector. Now, in this lecture, another important component of this traction vector or the traction force, how it will look like and how to compute that we will derive. So, traction vector computation for a CST element, within the CST element we can find it out. Now, to start with, we will just briefly I will tell what we have done. So, we have done the matrix form of this equation, that is your Ke elemental stiffness matrix into delta. So, that is equals to Fe. So, Fe, so this is for static problem. So, if you want to consider the dynamic problem, then you have to add the mass matrix too. So, that mass matrix Me and then your delta double dot. So, where the Fe has two components, one component is your due to body force, small Fe, and your traction vector that we have found out from the weak form. Now, the K is Me, also we know what is Me. So, Me is your integral, so rho h, so integral psi transpose psi. So, that we all know. Psi is the matrix which contains shift function, so dx dy, and now K is also we know, we have just derived in the last class. So, that is h into omega e. So, B transpose, B is the strain displacement matrix, C and B. C is your constitutive matrix, and Fe, small Fe is also the body force vector, that is H, that is over omega e, that is your psi transpose your Fx and Fy. So, two components of body force will be there. So, and your Qe, that is the traction component, that is also H. This is over the boundary of the element, that is gamma E. So, that is your psi transpose into Tx Ty. So, now computation of this has to be over line element. Now, this is over dx dy. So, here psi is also, we know, that is your delta vector contains the all degrees of freedom, that is your, for CST element you have 6 degrees of freedom total. So, for each node we have 2 degrees of freedom, 1, 2 and 3, and then you have this U1, V1, U2, V2 and U3, V3. So, these 6 degrees of freedom contains delta. So, now UV essentially which are function of xy. So, essentially what I mean is that u is a function of xy and v is also a function of xy. So, this is represented in psi shape function matrix into delta. So, now B is strain displacement matrix, which is again strain is B. So, computation of strain displacement matrix is also simple, that B is your the differential matrix, that is del del x, 0, 0 del del y, then your del del x, del del y, del del x. So, this is your differential matrix, then psi is your this thing shape function matrix. So, this is how we calculate, and then again sigma vector is your C into your strain. So, then again C is your C, and then you have B and then delta. So, this is how we replace it in the you can replace it in the weak form, or you can replace it in the virtual work statement, and considering the arbitrary variation you get this equation. Final equation is of this form. Now, computation of this computation of these matrices are very simple for triangular element. Linear constant strain triangle, that is CST, that because CST the all derivatives are constant. So, naturally B matrix will be a constant matrix. So, because since B is a constant matrix, strain will be constant. So, that is why it is called constant strain triangle. So, obviously constant strain triangle will have jumps between inter-element boundary. Now, the important part that we are going to discuss here, that this quantity, this traction vector, is actually we have to compute over the boundary of the element, not over inside the element. So, let us consider, so now before that let me also tell this body force term. So, body force term is essentially you can compute that Fx and Fy if you have, then you can compute it very easily. But in case of constant Fx and Fy, that is if I take Fx is f of x of 0 and Fy is, that is a constant value y of 0. So, then this Fe form is very easy to compute, because this will look like this. This is over omega e psi transpose, and then f of x of 0, f of y of 0. So, this is dx and dy. Remember, this is not a function of x, but this is a function of x and y. So, this is not a function of x and y, but this is a function of x and y. So, you substitute the psi matrix that we know, that is psi matrix is our 2 by 6 matrix, that is psi 1 0, psi 2 0 and psi 3 0, then 0 psi 1 0, psi 2 0, psi 3. So, this is my psi matrix, and psi I is represented as 1 by 2a e. The a is the area of the element, and then alpha I plus beta I x plus gamma I y. So, now alpha I, beta I and gamma I, we know that alpha I is yi xi, like that we can find out. Now, So if I integrate it, so it's a linear function because this psi matrix is a linear in x and y. So if I integrate it over the constant this thing, then the global form of this psi will look like this, that is A by H by 3 into your 6 cross 1 vector, that is f of x0, f of y0, f of x0, f of y0, f of x0, f of y0. So this is, we can find out the integration, because your integration will happen as x dx dy, y dx dy, like this the integration will come. So if you integrate it finally over the domain, that is over the area, and then this will be your constant force vector. So now this is fine, but if the fx and fy is not constant, if fx and fy are function of x and y, then obviously you have to integrate the terms involved in fx and fy also, which may be dependent on x and y. So this can also be performed. Now the next part is that how to compute the traction vector, because in the final equilibrium, elemental equilibrium equation, which is this equation, so elemental equilibrium equation, you need to compute body force as well as the traction component. So now we will discuss how to compute the traction component. So to compute the traction, let me just draw a simple problem, so that just a test problem, so that you can understand the whole procedure. So this is a something like this. So I'm just drawing it for your understanding. Now suppose this is my discretization of the element, so discretization of the domain through triangular element. So now this is my, so this is a structure, so this structure may have some boundary condition here and there, so this may have the here and there, so this also may be something like this may be there. So now there is a force in this structure, so which is normal to this part. So suppose this can be a uniformly distributed force, this can be a triangular force, this can be a variable force, or any other force. So let us take for the simplicity, let us take the triangular force. So let me take this as a triangular distribution of the force. So that is your this. So now this force is perpendicular to this face of the body. So in that case, how to compute the traction vector? So the process will be same, only thing is that this force is variable. So this part, let us say this is your Q0, and let us now see the discretization of the elements. So 1, 2, 3, 4, 5, 6, 7, 8. Now this all the elements, so this is say element number 1, 2, 3, 4, 5, 6, 7. So all 7 element and you have 8 nodes. So total degrees of freedom is 9. Total degrees of freedom is 16. Now among 16, some of the degrees of freedom are restrained, so you know the value, and this is obviously a traction boundary. These are traction boundaries because there is no traction force, but only here this is also a traction boundary, but this boundary there is a force acting on the body, which is in the form of traction. So I will now if I consider the local coordinate system of this element, that is 1, 2, 3. Now this 1, 2, 3 two sides is having a traction force. So now before we go to here, so here there is a, this force is normal to this line. So this is also the global coordinate system is our this is my global coordinate system, xy system. So you have this angle, if I take this angle as theta, so this is 90 minus theta. So this angle is 90 minus theta. So with this 90 minus theta, it is inclined with the global traction. So now if I take this thing here, so in a local coordinate system, I have to map it to compute this in the computation. But once I map it, then this has to be rotated, this has to be transformed to the global coordinate system from local to global. And how to do the from local to global? Because we know that from our beam or not beam, for 2D frame element, when we did 2D frame element, then probably you have noticed that if you have a inclined member in a frame element, then what you do, basically you have suppose this is a frame element, then you have u1, v1 and theta 1, then you have u2, v2, or probably you have used w, so w1, w2 and theta 2. So these are the degrees of freedom associated with this. u1 is along the axial x direction, w1 is the vertical. So for 2D frame I am just discussing. Then how you compute everything, the force vector in the local coordinate system, that is your x bar, y bar coordinate system. This is your x bar, this is your y bar, and then you convert this thing in the local you convert this thing in the global system, that is your, this is x and this is y. So how to convert this? If this angle is alpha, then what you did is essentially if the traction vector or the force vector is q e bar, then that is your x bar and y bar system, then you from this x bar y bar system to xy system, you multiply with a transpose, that is rotation matrix transpose, that you multiply to get the this not bar, that is in global coordinate system. So that is your QE global system in XY system. So what is this RE? This RE is your if you remember, that is cos alpha, sin alpha 0, then sin alpha minus sin alpha, cos alpha 0, then 0, 0, 1, and then again you have the same thing, that is your cos alpha, sin alpha 0, then minus sin alpha, cos alpha 0, then 0, 0, 1. So this is your, and these are all zeros, because this probably you have done it, how to rotate it. So this is also 0, 0, 0, 0, 0, 0, and then 0, 0, 0. So only this is a block rotation matrix. So this is one block and this is one block. This is corresponding to u1 v1 u1 w1 theta 1, and this is corresponds to u2 w2 theta 2. So this you pre-multiply with the force vector to get the global force vector. Now here the same case, but here we don't have theta because theta is essentially your z direction rotation, means about z. So that means it doesn't change if the angle changes, member angle changes with the global xy, rotation doesn't change. So that's why it is 1 here. Now if you do this for this problem, suppose this problem in this case, if I generalize it, so suppose this is my this thing, now this is making an angle theta or alpha, let us say. So what are the degrees of freedom you have? You have u1 v1 and u2 v2. So you have 4 degrees of freedom. So naturally only this part of the matrix is activated, other part will be not activated. Now remember one thing, that you have 3 by 3 matrices, you have 6 degrees of freedom. So now you have this triangle is something like this. So so you have U2, you have this quantity. So there is another node, that is U3 V3. So even though this node is not participating in computation of traction directly, because this may be an internal load, so you have three nodes. So you have 6 degrees of freedom total. So now if I this QE for this case will be your QE again RE transpose QE bar. So QE bar. So now RE here is same, but this one term will not be there. So this will be now my cos alpha, sin alpha, then minus sin alpha, cos alpha, then cos alpha, sin alpha, then sin alpha, cos alpha, then sin alpha, cos alpha, sin alpha, minus sin alpha, cos alpha. So this will be the case. The other terms will be 0. So basically it is a if there is a n number of nodes, so this is a 2n cross 2n matrix. So this that means 3 number of nodes. So this is a 6 cross 6 matrix. Naturally, because this traction vector will be 6 cross 1 vector. So this is also a 6 cross vector. So this is also a 6 cross 6 matrix. So finally your global traction vector will be 6 cross 6 matrix, 6 cross 1 vector. So now once I know this, so here also it is the case, it is the alpha is here 90 minus theta. So first what we will do, we will compute this thing in the local coordinate system. Now to calculate this quantity or this traction contribution, we have to bring it to the local coordinate system. Now in the local coordinate system, that is your that is q bar E. Now this q bar E we have to compute. Now to compute this, let me bring this element here. So now this is my 3 2 line, that is here my 3 2 is my coordinate, that is of this triangle number 7 here. Now here we know that is x3 y3 is its coordinate. So x2 y2 is its coordinate. Now here I have a triangular load. So this triangular load is vertically downward. So that means the contribution is negative. So now if I now impose a local coordinate system, which is along this is the normal, and along this is my S. So now this point, the point 3 contributes to S equals to 0, and point 2 is S equals to the length of this side 3 2. So that is L32. Now this L32 if I have to find out, so here one important thing is that this part you have to compute only in this L32 part, because the other 2 part will cancel out from this thing. So now this L32, so your integral is essentially your this integral, that means your q bar E will be your h integral 0 to L32. So now this will be your psi transpose. Now this will be your Tn and Ts. So this is my Tn obviously, this is a function of s and t, s and n. So s and n will be my this thing, and ds is my along this line I want to integrate. Now here what is the other two contribution, that is the length of 1 2 and 3 1, because these are inner side of this triangle, so that will cancels out from the neighboring contribution from the neighboring element. Now but if you look carefully that what is my Tn here, so Tn, this quantity, the maximum height of this intensity of this load is Q0. I believe I have this, yes, Q0. So this is my Q0. Now naturally I can say my Tn is actually minus, because it is on the negative side, Q0 S into L2 by 3 2. So from here, so 3 2 is my length of this thing. So Q0 is L32, that is my Tn. Now so this is fine, this I can, and Ts is actually 0. So because there is no nothing there, so Ts I can make it 0. So now phi, if you see phi, this phi contains your phi 1, phi 2, phi 3, all these things. Now these things are in terms of x and y. So now you have changed your coordinate system locally, so you have to change x and y locally also. So that means your phi 1, phi 2 and phi 3, which is a function of x, y and constants alpha 1, alpha 2, alpha 3 and beta 1, beta 2, beta 3 and gamma 1, gamma 2, gamma 3. Those constants are fine, but x and y we have to change it s and n coordinate system. Now so let me again write it my x as 3 parameter. So x is actually a1 plus b1 s and c1 n, and y is actually a2 plus b2 s plus c2 n. Now see what we want, our element is at n equals to 0, we have that element. So I don't need to compute these things actually. So my x and y variation actually along s only. So so that's what I need basically. You can compute obviously if you consider the third triangle, so which is here probably. So if you know the distance from here, what is the s and what is the s minus n, then you can compute the n also. That is a different issue, but we don't need that, because we need only the variation of the traction along the s axis. So along n axis there is no force, so there is nothing. So now so what we have basically, we have two constants, a1 b1 and a2 b2 for x and y. Now we have two boundary conditions also. So what is those boundary condition? Because at s equals to 0 we have x equals to x3 and y equals to y3. So basically this is for n equals to 0 and s equals to 0 and y equals to y3. So this is my one condition by which I can solve the find out the constant. And similarly for n equals to 0 and s equals to L32, that is at this point. So I have x equals to x2 and y equals to y2. Now with this, if I substitute it here, then my x x will look like this. That is my a1 will be x3 and a2 will be y3, and then b1 is essentially x2 minus x3 divided by L23, right? So that is my b1, and similarly b2 will be y2 minus y3 by L23, right? So now my x is I can simply write as my x3 plus b1 is x2 minus x3 by L23 into s. So basically it is x3 into 1 minus L23 and plus x2 into s by L23. If you look carefully, you will see that it is representing a linear one-dimensional Lagrange polynomial. So because x3 and x2, y3 and y3 and y2 are essentially constant. So now this is y2 and this is L by 23, right, or 32, whatever you call. So that basically the length of this side. Now once we know this, then my phi 1, phi 1, phi 2 and phi 3 I have to find out with this substitution. So basically psi I is 1 by 2 AE into alpha I plus beta I x plus gamma I y. Now this is essentially 1 by 2 AE, then alpha I plus beta I is your constant, so beta I, then x I will substitute this, so that is my x3 into 1 minus L23 plus x2 into s by L23, right, and then gamma I is similarly y3 into 1 minus s by L23 plus y2 into s by L23, right. So this is my gamma psi I. So if I compute this thing, if I do some manipulation, you will see that psi 3 will come as 1 minus s by L23 and psi 2 is s by L23 and then psi 1 will be your 0. You will see this. So now basically this is same as linear linear Lagrange polynomial for one-dimensional shape function, which is natural because the variation is essentially linear here. Now if you do this, so our objective now is to find out this quantity. So to find out this quantity, if I now multiply this psi transpose, that is this quantity with Tn and Ts, so this I can write now h integral 0 to L32. So psi is basically psi 1 0, psi 2 0, psi 3 0, and then 0 psi 1 0, psi 2, then 0 psi 3. Then this is my Ts is 0, so naturally Tn 0. So this is my S. So if I multiply, this is transpose. So this will be my 6 cross 2 matrix. So only this part will be. So if I multiply this, then what will happen? This will be essentially, if I now substitute my phi 1, psi 2 and psi 3, which is from here. So if I now substitute this quantity to there, then after integration I will get something like this, that is minus L32 Q0. So Q0 is my intensity, maximum intensity divided by 6. Then you have this, so which is 0 0 2 0 1 0. So this will be after integration, because this is a Tn is a function of where I have substituted also Tn is minus So that's why it is minus Q0S by L32. So this is also I have substituted here. So and this is transpose, so this is a 6 cross 1 vector. Now once I know this QE bar, then I have to find out this QE. So to find out QE, I have to pre-multiply with the rotation matrix transpose. So this rotation matrix transpose is essentially your how much it is angle with the how much it is angle with the this quantity. Just a second, yeah. So this is 90 minus theta. So naturally, if I substitute this alpha equals to 90 minus theta, that is alpha equals to 90 minus theta. So then I have this cos alpha sin alpha minus sin alpha cos alpha. So once I do that, that is your Q bar. QE is your rotation matrix transpose into Q bar E. So once I do that, then I will get the answer like this, that is L3 by 2 Q0 by 6 into your 0 0 2 cos theta 2 sin theta, I believe. So 2 sin theta. So it is just matrix multiplication, cos theta, then sin theta, cos theta. So this is how essentially you calculate the traction vector. So now the important point is here that for this kind of linear element, it represents the linear polynomial in one dimension. So remember, if this quantity, this is side instead of 3 2, if I do it from 2 3 as is, that is, if I take my axis as this. So suppose if I start taking my axis from here instead of from here to here, so that is also possible. So this is my N and this is my S. If I start taking it, then phi 2 will be 1 minus S by L3, psi 2 will be 1 minus S by L23, and then psi 3 is your S by L3 23, but your psi 1 will be always 0 because the N variation we are not considering. So now this is how we calculate the traction variable. So now if a triangle has different sides which is outside, so suppose this is my side. So now this is a general triangle in a system. So if you have, this is my side number 1 2 3, then you have this vector perpendicular, and also you have this vector perpendicular to this. So this is all, this can also be calculated. So here in this triangle, essentially your QE will have 3 quantity, that is integral of lambda E. So this is H, so psi transpose into your Tx Ty. So this quantity can be devised as 3 boundaries. So suppose you have this, then you have lambda 1, that is this thing. So lambda 1, there is no force, so you don't need to compute lambda 1. So only lambda 2 this side. So this side, so lambda 2. So sorry, gamma 2, gamma 2, and this side gamma 3. So H into psi transpose Tx Ty into ds plus H into gamma 3 psi transpose Tx Ty. So these two you have to find out only. Now finding out this, that is this boundary. So if I take, this is my lambda 2, then this boundary I can assign my axis from here and here. Again, I will compute psi 1, psi 2, psi 3 according to this local axis, and then for gamma 3 I can assign another axis from here to here, and then I can compute psi 1, psi 2, psi 3 according to this axis and to compute the this integral. So these two integrals I can individually compute, there is no problem. Only thing is that this transformation has to be proper, because this probably is, if I take the global axis, then this theta I have to notice, and if I take this axis, then this theta I have to notice. So these two theta, according to the transformation, I have to pre-multiply with the local traction vector. So with this traction vector I can transfer with the local transform vector, I can transfer to the global, and then I finally get the elemental equation or the elemental equilibrium equation, which is here. So once I know the elemental equilibrium equation, the rest of the procedure is very simple. Considering the connectivity of the element, you have to assemble it for the all element, and then you have to solve it after putting the Dirichlet boundary condition. So this is all. This is the matrix formulation. So in this in the next class I will try to solve some of the problem for this exercise. So I stop here. So in the next class we'll try to solve some problem. So thank you.